Okay. Um, this is going to be a series of videos, um, and I'm combining chapters 26 and 27, where we are going to study circuits. So some of the things I'm really going to gloss over. So you have a PowerPoint in front of you. Theoretically, you have it open in front of you, and I don't have it open in front of me. I'm trying to do this whole thing out of my head. I'm just going to hit the major points. These are the points that I imagine at this place in May you are ready to be finished. But these are the points that my soul, it's bothering my soul that I'm sending you to college without having. Because just with everything that has gone on this last term, we certainly didn't we did well with what we got through, but we didn't get through as much as I had planned before coronavirus hit. Um, so there are a couple of things that I just want to really make sure everybody gets before you finally totally 100% check out. You might be very close to there right now, but bear with me. We're almost at the end. Now, those of you who are taking the AP exam, if you are really trying to pass this one, we'll be kind of talking in our review sessions, but some of the things I'm glossing over, you don't want to gloss over. So I included in the PowerPoint everything that I think is fair game for you people. And I'm happy to talk through concepts with you, but the textbook also does a really great job of explaining some of those things. Again, I think you're just going to see them as conceptual questions primarily, but just FYI, so that's kind of how I laid out this PowerPoint. So you'll notice, all of you, that I'm skipping some things, and if I skip it, go ahead and skip through. But if you're taking the AP exam and you're putting in some effort on the E&M part of it, then pay attention to those things. Okay, so that's what I have to say about circuits, so we're just going to get into it. And I'll kind of keep a running list of some of the concepts that you need to know. And we'll see how far we get. Okay, so the first thing that comes up in this chapter 26, is that they finally throw out the word current. And so I've kind of been using this word, but current is the rate at which flow charge, or oh my gosh, the rate at which charge flows. We indicate current with the letter I. I stands for current, and you know, this is not an equation we'll necessarily use, but if I had some function, Q, remember, is charge, T is obviously time. If I had some function for how charge is moving, how it changes with respect to time, so again, that rate at which it flows is how I would define current. So we're very rarely actually calculating current. If we were, they would give you Q and T, you would divide essentially. It's just more of a thing that we will see coming up. Current is measured in amperes, which is actually one of the SI units of measure. So you, somewhere in junior high, maybe you memorized it and you didn't even know what it was. So current is measured in amperes. Just to give you an idea of scale, a lot of the amount of current that's flowing through the circuits in your home depends on what you do. Like, did you plug in a hairdryer or a little light bulb? But most of the circuits running in your home are running like at 22 amps. So that's kind of a fair amount of current. That's something that would be dangerous for you. Like if you stuck your hand in the middle of that, that could be dangerous. So current, again, rate at which charge flows. How do we get charge flowing? Well, the very simplest kind of circuit we can have will have a voltage source. Typically, when we're in a lab, which we're not, but when you're doing these virtual labs, you would have, this indicates your voltage source, right? Typically that would be a battery. Now in your home, it's a little bit different, like you're plugging in to your voltage source. And you notice that there's two prongs on it, right? So one is a positive terminal, so we indicate that, and one is a negative terminal. And in a battery, how would they produce those positive and negative ends? It's chemistry. I don't know if you talked about how how different acids can behave as batteries, maybe in a chemistry class. You had a solution and a teacher put like a light bulb in, it had little plug things on it, and the light bulb would turn on, and it was amazing. So batteries are gonna be one of the things I gloss over just because of time. But they use chemistry to produce an end, or what we would say is a terminal, that has a high positive potential, electric potential, and then one that has a high negative potential. So, if I have a loop of wire, this is the simplest circuit we could have. If I have a loop of wire like this and I have charge, we diagram charge the way that positive charges would move. So, which is really irritating because everything that's happening in your house and everywhere is really negative charges. But if I had a positive charge, it would move away from the positive terminal of the battery because it's being repelled by it, right? And it wants to get to the negative terminal because it's attracted to it. So it's going to move in this loop all the way around. The higher the electric potential, the faster those charges could move, which hopefully makes some sense. It's like kind of, again, you have more potential energy, which means you have more potential for motion. So this flowing of charge from one terminal of the battery to the next, this is what we would call current, right? So again, we can measure that flow of charge, and that is what we ID as current. So there's a lot of different things you can do with current. If you're reading along with me in the textbook, there's some things that I'm skipping over. One of the things is called current density. And so we're just going to move from here right on into the next thing you could put into a circuit, and that is resistance. Or we call something with resistance is called a resistor. So a resistor is anything that would slow this flow of charge down. So anything that's going to slow down current. It's kind of like, this might be a poor analogy, but it's a little bit like friction, but for electricity. So things that would slow charge down are called resistors. They put resistance into that flow. If a resistor is put into a circuit, well, let me say this first, like any wire is going to cause some resistance, right? Because as charge flows through this wire, the charge is going to interact a little bit with the wire, the actual physical wire itself, because the wire is made out of atoms, so it has some charges. And so just that slight interaction causes a little bit of resistance. So there's always what we call internal resistance in wires, and actually even batteries, as the charge is flowing from one terminal to the next. But I can put in a resistor, a physical resistor. And so the symbol for that in a circuit is this. And there's not a set number of squiggles, but that's what it is. And so again, a resistor is something I'm going to put into a circuit to slow down charge. Sometimes charges slow down because it's like doing something. So one kind of resistor I could put in is a light bulb. And so we again do this virtual lab, and I'm going to on Wednesday, so hopefully you're listening to me and watching this before Wednesday. On Wednesday in class, we'll have class again in my scary basement because I can get it nice and dark down here. And I have some light bulbs. Actually, there was like one thing I thought to snag, and I have a battery and we can build a simple circuit, but I have some light bulbs, and we'll look at how these things are connected in series or parallel, which is something I'm going to talk about in a few minutes. But these light bulbs are resistors. So if I were going to draw a circuit diagram for these light bulbs, this symbol would indicate there's a light bulb there, for instance. You could plug in, I talked about a hairdryer a minute ago. If you plug a hairdryer in to your bathroom, that's like putting a resistor in the circuit that your bathroom electricity runs on. So resistors, again, things that slow down the flow of charge. And so if I were to put one in here, there's my resistor. Resistors are measured in units of ohms, named after the guy who studied them. He came up with a law called Ohm's law. And if you have a resistor has a physical property called resistance. Okay, so just like when we talked about capacitors, I said a capacitor is a physical thing you put into a circuit. So these two plates separated by some distance, very, very small distance, you usually don't see it. And they might be wrapped up into a certain shape or whatever. But a capacitor stores charge in a certain way, right? So we said Q is equal to C times V. And if I know Q and I know V, I can find C. But you can also find its capacitance would be a physical property of the capacitor itself. So it depends on the area of the plates you have that are storing the charge, and then the distance between the two plates. Kind of the same idea here. A resistor, usually, you know, you'll see this as I do some things, but a lot of times they'll give me a value. They'll say, oh, I have a 100 ohm resistor I put into a circuit, and that's that. But the resistance of something, particularly wire, is a physical property of the thing itself. And so we say resistance is equal to rho times L over A, where rho, this is a resistivity constant, so like a physical property of the material. So it's some value for copper, different value for aluminum, just et cetera, et cetera. So this is a resistivity constant. L would be the length of whatever you have that's going to have some resistance. So think about it logically, like if I have a wire that's put into this circuit, if this wire is 1 meter long versus 10 meters long, the longer it is, the more places for this interaction that's slowing down the flow of charge to happen, right? So resistance or resistivity, you see it in the book, is directly related to the length of usually wire, whatever the material is. It is also inversely related to A. Now, what do we mean by A? A is the cross-sectional area of, again, let's say wire. It's almost always wire we're using. So if you've ever gone to the hardware store to get wire, don't know if you have, it's different gauge wire, which just tells you how thick it is. So the thicker wire, so if we look at this, the higher A gives us a lower R and vice versa. The higher A, because think about it like a hose, it's a bigger hose, so more charge can flow through more quickly. Those low A's, then it's going to flow a little bit more slowly. You're going to have more resistance. So, so you can find the resistivity. This is typically, again, used for wires. So you can find the resistivity if they give you the constant, the length, the area. So when using this equation, almost without exception, it's like a plug and chug thing, right? So they'll give you these different values and say, find the resistance of 10 meters of copper wire with a radius of 1 millimeter. And then they'll give you the resistivity constant and you plug and chug. So these are the basic properties of resistors. Now this guy named Ohm, he studied resistors and simple circuits. So when I say simple circuit, I'm talking something like this, where you have a voltage source, so a battery, some wire, and a resistor. And what he wanted to do was look at how three things were related. So the three, oh, I should have worn, I have such a nerdy t-shirt, like with Ohm's law on it. I'm going to wear it for the next lecture. Okay, anyways, he wanted to look at how V, I, and R are related. And this really, I mean, some people, this is a really, really important law. You might compare it to Newton's second law, so F equals ma. Like, think about how much of mechanics hinged on that. And here we're on like the second to last day of class, and I'm going to give you the big one for electricity. So V, I, and R, he looks at how they are related. And so he's going to take two things at a time. He, in the same way that we, with Newton's laws, sorry, American Girl, Donald Trump was in the way. With Newton's laws, we want to look at how F affected A and then how M affected A. Here we're going to look at how each thing affects I, the rate of charge, or the rate of flow of charge, current. So if we keep our resistance or resistivity of the circuit constant, so we're not going to mess with that, we want to look at how V and I are related. Now he did this experimentally, and you're going to mess around with it a little bit in your online lab. But let's just think about it intuitively. If I increase my potential here, what happens to the rate of charge flow? So if I go from 10 volts to 20 volts to 100 volts to 1,000 volts, what do we expect to happen to the current? And I hope we would say we expect the current to go up in the same way that the electric potential does, right? Because electric potential, remember, electric potential and electric potential energy are two different things, but they are absolutely directly related. So the more electric potential I have, the more potential energy I have, which means I have more potential for motion. I can get a higher kinetic energy going on in this thing. So we say that V and I are directly related. Now, let's say we hold V constant and we want to look at I and R. So let's say that I increase my resistance. Now, resistance by its very definition is resistance to flow. It's something that's slowing down the flow of current, of charge. So if I have higher R, I'm going to expect to see my rate of flow of charge go down, right? So we would say that I and R have an inverse relationship. Now, Ohm had to do a lot of experimentation to see, like, what can I put an equal sign in here? Like, is there some constant that comes out of this or what? And so, again, I'm not doing it justice because we're on the rush, but there's no constant needed. So, if I put this all together, again, it was experimentally proven. I can say I is equal to V divided by R. So I is directly related to electric potential, inversely related to resistance. And we often see that rewritten, because who likes a fraction, as V is equal to I times R. This is Ohm's law, and it is one of the, I mean, when in doubt, throw it on your AP test. When in doubt next year in college, write it down. It is just used so often. And the nice thing here, these are not vectors. So where when we have that equation, sum of all forces is equal to m times a, it looks so easy, right? And then it turns out you can do some super complex problems with it. This, we can handle some complex circuits and tie this in at the end. So they can get tricky. But when using this equation, it's always going to be as easy as it looks. It really is. So this is, I'm going to add it over here to my list, Ohm's law. This is one of those really important equations. V is equal to I times R. Again, V is going to be measured in volts, I is measured in amps, and R is measured in ohms. Okay. And then the last thing in chapter 26, keep in mind I'm skipping a lot of things, but the last thing in chapter 26 that's really important to hit before we get into the types of circuits is how we can calculate power in a circuit. So power, I'm just going to give you the equation, and this is one that is often given on equation sheets. P is equal to I times V. So power in a circuit is measured the same way power in mechanics was. It's in units of watts. And it's not that you can't see it as intuitively here as we did when we studied mechanics, but it conceptually means the same thing. Oh, sorry, doing laundry. It's awkwardly loud for a second. I'll just pause. Let you listen to my laundry flow. And well, maybe I'll just go. So power is telling us the rate at which work is done, right? So there it goes. The rate at which work is done. So in mechanics, we would say power is literally work divided by time. But another way we wrote power is that it was equal to force times velocity. So that was something we saw with like literal mechanical motion. So power means the same thing really with electricity conceptually. It's telling us the rate at which current is doing something. And you know, I'm not going to derive it, but it's the same thing. It's the rate at which electrical work is done. But the most commonly used equation is P is equal to I times V. Now you will see other versions of this equation, but they all come from just messing around with Ohm's law. So let's say, for instance, that I didn't know V. Let's say I have a circuit and I know the current running through it and I know the resistance in it, but I don't know the electric potential. That's rare, but let's say that happened. Well, I know V is I times R, so I can say P is equal to I times V, which is I times R. So it's I squared times R. That's one way to write it. More commonly, you might not know R, which is why this is the one we most often use. But you could also have a situation where you don't know I. So you could say P is equal to, well, what is I? I is V over R times V. So V squared over R. So I have these three real versions of the power equation. But again, this is the only one that's going to be listed, and this is the only one that really needs to be in your head or you need to be comfortable with. And then you just rearrange as needed based on what you're given. So power is given in watts. Power can be used, this is an interesting thing you can do with it, to figure out if your fuse is going to blow. So I'm making up this problem off the top of my head, and now I'll be embarrassed. If you check me, I forget if the circuits in your home, they're going to blow a fuse somewhere between 20 and 22 amps. This is exhaustion. I don't hear myself, so I can Google it. Let's say 22 amps. So in your house, you all have, it's actually right here in the other room for me because I'm in my basement. In your house, you have a box, your service box. And, oh my gosh, sorry about the laundry. And there's all these fuses, right? And that is one of the biggest ways to keep your home safe from electrical fires. So you hear a lot less about electrical fires nowadays than you would have 50 years ago. And so, and probably, I hope at some point in your life you've blown a fuse and you've had to go downstairs to that box and figure out which one you've blown and you've had to reset it. If not, learn that skill before you get your first apartment. But your home has, so most of the circuits in your home have a potential of 120 volts. So like when you plug something into an outlet, the potential between the two prongs is 120 volts. What happened?
There was a tube right here.
Okay, good. Did you wake up, Asher?
No, he was already home.
Sorry. So V is 120 volts, and most of the time, your thing should blow again. Let's just say 22 amps. It might be 20. It's somewhere close to that. And so if you go over, if you start to plug too many things into your circuit, you have all these little circuits in your home. If you've blown fuses, you have an idea of where those circuits are. So let's say, for instance, the bathroom, like you and your sister and your mom are all trying to dry your hair. You all plug in, somebody plugs in a straightener, two of you plug in a hairdryer, and somebody has the radio on like a plug-in radio, not your cell phone. So those things all draw a certain amount of power, right? They're using electricity to do work, and if they need too much I, so if it would exceed 22, then that is making current flow really fast. And as current flows faster and faster and faster, it produces heat, essentially. And it can produce fire. So it's not at 22, that's well below the threshold, but that's why we want our homes safe. So if I said you have three things and they're plugged in, so you have a hair dryer, and its power is, I'm not picking really good numbers here, 1500 watts. And you have a straightener. I don't know what a straightener would be. This 1500 is probably pretty reasonable. Straightener, I don't know, 800 watts. You have a radio. It's 140 watts. And so my question is, will that blow a fuse? Okay, so I say, well, P is equal to I times V. I know I have a certain power. My power is 1500 plus 800 plus 140. So I'm going to cheat and use my calculator. So my total power that I need to operate these three things is 2440 watts. This is equal to current. Now what I want to do is find the current. I want to see if it's bigger or smaller than this threshold. And all of these things are plugged into regular plugs in my wall, 120 volts. So I just solve for I using the power equation. This is one of the most common ways you would use this equation. And I get 20.3. So if I'm right on my guess of 22, then I'm right there, but I'm under the threshold, so everything will operate fine. Now let's say I come along and somewhere in the same circuit, you know how sometimes if you blow a fuse, like two rooms will go out at the same time. Let's say I plug in a vacuum, that's like the kiss of death. I plug in a vacuum and that's 1000 watts. you don't even have to solve it. You can see that it's just going to take me right over. But now my power's at 3,440 watts, still plugged into the same outlets, right? I mean, you know, all the different outlets, but they all have the same potential. So my current jumps way up and becomes 28.6, 20.7 amps. Now here, I know that I've exceeded what is the electrical code in our homes in America. So at that point, as soon as I press on the, you know, it's not when you plug it in, it's not pulling anything. But as soon as you turn it on, the whole circuit's just gonna go, and everything turns off. That's on that loop, and then you have to unplug everything and go downstairs and into your fuse box and reset the fuse. So that's one of the most common ways we use power with a problem. So it's a really nice sample problem for power. So the problems that you're solving for Friday, the ones that are out of chapter 26 are really simple problems. They're basics working with current, basic Ohm's law, basic power type stuff, basic resistivity, very much like plug and chug, just getting comfortable looking at these equations and what kind of situations they might apply to. Now I'm going to make a second video here in a second, and that one will get into a little bit more of the complexities of circuits.